All right, I would like to welcome everyone to another Zoom session for Engineering 200, Engineering Mechanics and Statics. Today is July 1st, Wednesday, July 1st. Okay. I'd like to go over two more sections of chapter 4, okay, two sections. The concept of chapter 4, section 4.7 and 4.8 are together, okay, together. That covers a language of simplification of force and the resultant moment and their further simplification. What does it mean? It means that in a structure, we might have a number of forces acting on the surface, or we have a free vector or free moment instead of vector. I'll say free moment or external torque applied to that structure or the two-dimensional force systems that is provided, or we can say a beam. We have a bridge or we have a beam that is simply supported and we wanted to simplify all the forces that are applied to the surface of that beam to a single resultant force, okay, single resultant force. And we wanted to know the location of the resultant force with respect to a left support, okay, left support. I mean, we can say right support, but it says we go from left to right, so it's better to say left support, okay? If it says right support, 1 minus that, no problem. So then from section 4.7, 4.8, we're gonna go to 4.9, and that is distributed load, or we call it loading diagram, whether it's a rectangular uniform loading diagrams or triangular loading diagram, or from calculus, we have a, we have a functions. They give us a function f of x, and we have a loading diagram, and if we know the limit of integrals, we can integrate the area under the curve, and we're gonna end up with resultant force, which is equivalent to the total area under this curve, okay, which we call it shaded area, okay, shaded area, or where the load is applied, okay. We have a maybe non-uniform load or uniform load, whatever the load is given. If we know the function, we can integrate, and then we can find the location of the resultant force, because we have all this single force that is applied to the surface of a beam at a different increment, okay? Say we have a 6-foot span of a beam, and we wanted to know where the resultant force is going to apply. And the resultant force is going to pass through centroid of that geometric shape. Centroid, okay? We're gonna be talking about centroid all the way throughout this course, okay? Where we call it the geometric center or mass center, or where the load, the total load is going to be applied at the center of that loading diagram. And we're gonna go over that, okay? So put your seatbelt on. I'm gonna just explain all that, okay? All right, so we have to understand the effect of moving a force, because in a laboratory setting, which I teach, I call it mechanics of materials class, we have a force or the load in the midspan of a beam, and we wanted to know the amount of deflection of the beam. But what will happen if we move the load to different location? What will be the deflection of the beam? So that's what they call it, effect of moving a force, okay? That's what it is. Find an equivalent force. This is very important. Find an equivalent force and resultant moment. Sometimes the textbook call it coupled systems, okay? They call it coupled system. I just don't want you to get confused between the coupled moments which we have gone over on the previous section, which is the two forces with the same magnitude and opposite direction and separated by perpendicular distance. When we have a external torque or moment applied to a given beam or a structure, I can call that, it has a curved shape, okay? Curved shape, that's a moment. I call that free moment, okay? Free vector. Moment is a vector also, free moment. Like this blue one here, okay? See that this blue? That's a moment. So the resultant moment, if we have these two forces in here, look at this here, we have a force, say clockwise is positive, okay? F1 times D1 plus F2 times D2. Okay, let's see if I can see that. F1 times D2. So the resultant moment is that, and then the resultant force is the sum of the two forces. And where is acting in this situation is acting at point A. So it's acting at point A. So you have the loads apply on this beam, and the person is holding that beam or the stick, whatever you want to call that. So you're holding it, and then you have a load here, you have a load there, we know the distance. So we take the moment, the moment, for example, in this case, we have it clockwise. So we can just take the force times the distance, and that gives us the moment for each case. All right, beautiful. All right, let's go to the next one. Let's say we have traffic lights, and it has a weight, okay, W1, which is given, and W2, and we know the distance for W1 to the where the post is or the column is on the street somewhere, okay? So you can say, oh, okay, I can find the moment of these weights. I will say W1 times D1 plus W2 times D2. So we're gonna have the resultant weight, which is the sum of W1 and W2. And the resultant moment about point O will be the product of the W1 and D1 plus W2 D2. So where is going to act? Is going to act at this point where we have the beam is connected to that post, okay? Post. All right, so if the force system lies in the XY plane at 2D case, then the reduced equivalent system can be obtained using the following three scalar equation. So this is the fundamental, okay? FRX equals summation of all the forces in X direction. We have to apply that. You cannot make up your own, right? So this is the formula. Summation of FRY equals summation of all the forces along the y-axis. And then the MRO, okay, MRO, resultant moment about point O equals to sum of the moment, couple moment, C means couple, or all the free vectors, moment, external torque, or moment given. In most cases is zero, there is none, but there might have one, or you might have two or several, and plus some of the moment about point O. But there will be a situation that the question is, remember to determine the resultant force and also find the resultant moment and determine where the resultant force is going to be placed on that surface of the beam and the location. We wanted to know the location of the resultant force with respect to left support. So I have an example that I have put together, and I'm going to use the dot camera to show you that. Maybe let me just do that quickly. So this way, when I'm showing you example problem, it makes more sense, okay? Just bear with me a little bit, okay? Just bear with me, because this is my favorite. And then stop the share. And let me just go back to this here. I think I should be comfortable now. And I'm gonna go to, I already stopped the share, correct? I stopped the share, and all right, so do you see the share screen? No, I don't have.
Not yet.
Okay, Matt, do you see? No,
No.
not yet. Okay, let me see where I'm at. Right here. Choose virtual background. Yes, this is a virtual. Okay, there we go. That was the problem. Virtual background. Okay. Come on. All right. So, oops. Okay. All right, my friend. Just put your seatbelt on. I'm gonna go over this. This will clarify all those questions you might have. Okay. All right. So, typical question, exam question. It says replace the force or all the forces and free moment acting on the beam, on this beam, okay? Acting on this beam. I have a simply supported beam with a pin support and a ball support, and I have a concentrated load at the distance 1.5 meters from the left from point O. This surface of the beam is x-axis, see that x-axis, and this is the y-axis. All right, so we have 4 kilonewton. We have a free vector or moment, which is a 15 kilonewton meters, and is a free, okay, is a free vector. So it's placed on here somewhere, and you don't need to know where the location is because it's a free vector. So, and then we have another load, or it's an attention. It's like a cable is pulling in that direction, 8 kilonewton, and the slope is 345. And then we have the height of this bar or this crate or box that is sitting on this beam. It is 0.5 meters above the x-axis, okay? 0.5 meters above the x-axis. There we go, and that's an 8 kilonewton. We want to replace all these forces by a resultant force, which is Fry, Frx, and magnitude of the resultant, and the location of Fry, or the magnitude of the resultant force with respect to left support or point O, okay, that D, distant D. Because we don't know whether it's here, here, there, all this is equivalent to this. That's a simplification, okay, of the forces. So the question again, it says replace the force and a free moment or free vector acting on the beam by an equivalent force and determine where its line of action intersects the beam, and where the line of action intersects the beam measured from point O. Okay, there we go, measured from point O. Okay, let's see if I can move this to the side. And this is here. Okay, so we apply the summation of forces in x direction equals to Frx. This direction is positive. So we're going to have Frx, the resultant force along the x-axis, is going to be 8 kilonewton times the slope, which is 3/5 or 4.8 kilonewton. Okay, that's all we have for the x component. Resultant force along the y-axis is equivalent to sum of all the forces along the y-axis. So Fry, it's -4 because upward is positive, so downward is negative, so -4, plus if I resolve this into two components, this is one component, this is another component, okay? So we have the y component, which is 8 times 4/5. So you add and subtract, you get 2.4 kilonewton, okay, kilonewton. Great, okay, so far so good. Then the magnitude of the resultant is the square root of square of each resultant force, square of each resultant force, and we take the square root and we get 5.37. The orientation of this magnitude of the resultant force is going to be defined by theta. What is theta? Theta is inverse tan of Fry divided by Frx, which is true, correct? This is Fry over Frx. That's a tangent. So you can easily determine the angle or the orientation of the magnitude of the resultant force on this beam, okay, on this beam. All right, so we already established somewhere an arbitrary location, Frx, because it came out to be positive, it goes in this direction, and Fry is positive, going upward, and I made the distance, an arbitrary distance d from this resultant force. remember on a previous, yesterday's lecture, the question was asked, which of those components, whether it's a couple moment or just a resultant force or couple force, which one has a moment as a moment effect? We know that the y component has the moment. The x component about 0.0 does not have a moment because it's a collinear, right? So, and the magnitude of the resultant has no moment, because remember we said every time we have a vector with an angle, we want to resolve it onto x and y component. So I've seen the student, they just use the magnitude of the resultant to find the location. Please do not use that. Use the y component, the FRY, because that has the moment, because, okay? All right. So then this is the fundamental formulas, okay? You can use that anytime they ask you to find the location of the resultant force on a surface of a beam with respect to left support. In this case, the left support is 0.0, right? 0.0. So if I call this is the fundamental formula, okay? Governing formula. Resultant moment about 0.0 is equal to sum of the moment about 0.0. If you use this formula, you won't go wrong, okay? This is the fundamental formula. Assuming counterclockwise to be positive, the sense of rotation when we are taking the moment, okay? Sense of rotation. So let's do this. Resultant moment. We go to resultant force. So resultant force FRY, which is 2.4 kilonewton, times the perpendicular distance. Okay, that makes sense? All right. Equals. Now, this is the resultant. This is the regular forces, okay? The right-hand side, it's a sum of the moment about 0.0 of all the forces. So we look at the original diagram. The left-hand side, we look at the simplified diagram, which is a resultant force that has been established on this axis of the beam, okay? All right, so actually the axis of the beam, we call it in the middle, which we call it a neutral axis. And if we wanted to calculate the stress at the neutral axis is 0. There is no stress at the, if we are dealing with, in a high level courses like solid mechanics, if they ask you, what is the stress at the centroid or the neutral axis of a beam? You say 0. But what about the stress if we move away from the neutral axis? The stress will increase. Okay, we have a higher stress. Also, in a solid mechanics, when I go back to the, to the actual, because I'm on a dog camera, I can show you something about the stress, okay? All right, so, which is a force per unit area, okay? Stress is a force per unit area. Pressure is a force per unit area, and they have a unit of Pascal or Newton per meter square. All right, so the left-hand side is what? Is from the resultant force. So the y component, okay, which is a FRY, okay, FRY times distance. And the right-hand side, you take the -4, okay, because the assumed sense is counterclockwise. This is -4 times 1.5, -4 times 1.5, and then we have the free vector. This is a torque, this is a moment, which is clockwise, opposite of what we assume. So we have to say -15 kilonewton meters. Minus the y component. The y component of this vector has it has both the FRX, oh, I'm sorry, this is 8 times 3/5, and then this is 8 times 4/5, okay? All right, so 8 times 4/5, all right, great. So the x component, if we use the sliding vector, okay, a sliding vector, slide this, and then about 0.0 is going to turn clockwise. So it's going to be -8 times 3/5, 8 times 3/5, times the perpendicular distance, which is 0.5, right? Times 0.5. Plus the y component, okay, this is a free vector, okay? I'm sorry, not a free vector, a sliding vector, okay? A sliding vector. is sliding. So it's gonna, the moment of that component of this vector 8 kilonewton, it has a counterclockwise sense of rotation. Okay, it's counterclockwise about 0.0. So we have plus 8 times 4/5 times 4.5, because the distance from here to here is 3 plus 1.5 is 4.5. Now solve for D, you end up with 2.25. That means the location, this location of the resultant force with respect to the left support is 2.25 meters. Okay, that is, I just wanted to, because when I teach on the, in class on just on the whiteboard, I like to explain this before I go and go through the PowerPoint. So this will clarify everything. Any questions? Okay, so that's what we have, and I'm going to remove go back to my normal share screen, which is, where am I, the share screen? Okay, all right, so it's going to be up here. I hope so. Okay, share. All right, so that's where we ended. And then I'm going to go to virtual background, and then I'm going to pick that one. Okay. All right, guys. So far, so good. All right, so you can see that. Here, when they're showing this formula, remember the formula I've shown you. I said the resultant moment about 0.0 is equal to sum of the moment about 0.0, which is this here. Assuming there is no, but in my example, there was a torque, correct? One free vector, so that's what this was, the minus 15 kilonewton meters. Okay. All right, so let's go to the example here, okay? Example. We have a beam with bunch of forces applied to this beam, and this beam is connected to this wall at point A. And we have 200 pounds, we have upward, and 100 pounds within a slope given, and 50 pounds with an angle 30 degrees. Okay. Now, here they're not asking you to find, it says location measured from A. Okay, they're asking you to find a location measured from A. So the same as my example problem. Okay, a 2D force system with geometry as shown, given. Find the equivalent resultant force and moment and equivalent resultant moment at A, and then the equivalent single force location measured from point A. They are saying that if you find the resultant forces with the Y component and the X component, and then you have a magnitude of the resultant, where that is located with respect to point A on this structure. Okay, all right, so let me just go here. And again, this is the simplified formula, which I have shown you that resultant moment about A, in this case about A, resultant moment about A, divided by FRY gives you the distance. So if you calculate the MRA separately and FRY, already you've done it separately, you take this value divided by this value, gives you the distance, the location. All right, so a location of the resultant force. All right, so we go FRX, summation FRX, or summation of forces in X direction equals FRX, which is 50. Here we have 50 sine of 30 degrees plus 100 times 3/5. You just resolve this into Y and X component because going in this direction is positive. So we have 85 pounds. FRY, upward positive 200 plus 500 cosine of 30 degrees minus, because this is going down, is minus 100 times 4/5. So we get 163.3. Perfect. MRA, resultant moment about point A, is going to be 200, counterclockwise sense of rotation is positive, counterclockwise. So 200 times 3 plus 50 cosine of 30 degrees times 9 minus, because this component here, the Y component, minus 100 times 4/5 times the perpendicular distance, which is 6. So you end up with 509.7. The magnitude of the resultant, we take the square root, which is 1/2. See that here? It says 1/2. So we have 85 squared plus 163.3 squared. Take the square root, you get 184. Okay. Now, theta, which is the orientation of that on the beam, they're not showing the equivalent resultant force, the free body diagram on this. Oh, they're showing now here. See, so that's the magnitude of the resultant. But the magnitude of the resultant is 184, but FRY is 163.3. FRX is going to be 85 going this way. So if I wanted to find the location of this magnitude of the resultant or the FRY or FRX, because they're sharing the same cord or tail, the same tail. So FRX, FRY. There we go. I know what MRA is, which is 509.7. I know what FRY is, which is 163.3. Therefore, I know the distance from this point to the point A is going to be 3.12. The line of action intersecting the axis of the beam at the distance 3.12 feet from this point. Okay, yeah. All right, so I just wanted to clarify. Everything you do now is going to follow the same principle, same language. Okay, there we go. I think I made it as clear as possible for you. Okay, all right, so. And then there are more. I'll leave it up to you to go over this. Okay, you have it because it's really, really simple. Okay, really simple. I just explained it to you what that was. Okay, so all you have to do is go through that, the same thing. And then they didn't really ask you to find the location. They just asked you to find the FRA and MRA for this example. Okay, no location. All right, so now if we have a 3D, I just wanted to get to this one. You have the force in Cartesian vector form, F1 and F2. So the question is for the given two forces applied to this pipe assembly. We want to find an equivalent resultant force and resultant moment at point O. We're going to use matrices, okay? Matrix symbol or approach to determine that the moment. So we know that FR resultant force, we can combine all the element of each force, okay? So I with I, J with J, K with K, so we have a resultant force. Then we have what? We have something called the position vector from point O to this point here for the force number 1, the tail, okay, the tail, which we have 1.5 I and 2J, okay? 1.5 I and 2J. And then for this force number 2, we have 1.5, we have 4 feet, 1.5 feet I, 4 feet J, and 2 feet K, okay, and 2 feet K. Is that clear? Clear. All right, so find FRO means the resultant force that is going to act at point O, no problem. Summation of forces I means it doesn't matter, maybe there is 5 forces, 3 forces, but it says I as an indicator. F1 plus F2, and the resultant moment about point O is sum of the moment C, it's a coupled moment if it exists, and then sum of the Ri cross Fi, which is a cross product. Okay, Ri is the position vector, and then Fi is the force. Okay. So we come here, we're going to add all those forces, the element of all those forces in terms of ijk. So we have FRO. There we go. -2, -20, -30, 25 minus 10 is 15, 20 plus 25 is 45. What is R1? Position vector from O to this F1, okay? Here, we have 1.5 I and then plus 2J. For R2, position vector for force number 2, 1.5 I, 4 feet, 4J, and plus 2K. So there we go, all right? So that's ready. Now that is ready, we say the resultant moment about point O is sum of the forces in terms of Cartesian vector form. We say R cross F, R1 cross F1, which is this here, plus R2 cross F2, which is this matrix here. So we expand this matrix, we end up with this. We expand this determinant of this matrix, and we end up with this here. Now we say 50 plus 30 is 80 because we want to find the resultant moment. Resultant moment is R cross F in Cartesian vector form. In a scalar, we say force times distance. Okay. All right, so, and that is what we have in here. Let me have a little bit of water. Okay, all right, so. All right, so any question? So this is really a very straightforward, not that, complicated. So don't make mistakes on this kind of work. All right, so now I'm going to stop this share. I have one more topic to cover. Then we have all the freedom, okay? All the freedom. So I'm gonna share the last slide or lecture note for chapter 4, which is section 4.9. Put your seatbelt on. Everybody can see this slide, correct? All right, so there we go. We're going to use a load intensity or the distributed load for this crate that is placed on this fork left. And we wanted to know where the resultant force is, which it passes through the geometric centroid of this shape, which is a rectangular shape. Okay, next. This is very important. Every time you have a surface, like a billboard, or you have the sign that you see on the freeway, which is, attached to a very strong post, because the wind, the pressure that comes from that wind is going to really remove that sign from their support because it's so powerful. The unit of pressure is Newton per meter square or Pascal. So in many situations, a surface area of a body is subjected to a distributed load. Such forces are caused by winds, fluids, or the weight of items on the body's surfaces. When you take two courses, okay, one is called solid mechanics, the other one they call it fluid mechanics. So you're going to be dealing with, in solid mechanics, you have a rigid body, and you wanted to determine the resultant force that apply to this surface, but you have only what? You have the pressure distribution, you convert the pressure distribution to load intensity, and then you convert load intensity to resultant force. And that's the question will be, okay? Resultant force. Because the unit of pressure is Newton per meter square, the unit of load intensity, we call it Newton per meters, and the unit for force is Newton. So fluid mechanics is a moving fluid, whether it's an external flow or internal flow. So you need a knowledge of statics, okay? Knowledge of statics to take care of the problems in fluid flow, okay? And then it's the most powerful concept if you have to take as a mechanical engineer a complete semester course in fluid mechanics and also thermodynamics and heat transfer. But I just went over thermofluid and heat transfer in 3 weeks at USD. So it was so much overwhelming amount of information trying to come in just the 3 weeks, and it was a stressful time, but I think we survived, correct? Matt, you survived. Great. All right, so please remember this section, the last section of chapter 4, is the one that is going to create problems for you if you don't pay attention, okay? If you don't pay attention, this is very tedious work. So we have a function, we have a pressure function because the pressure axis, x-axis, pressure is a function of x. So we wanted to know where the force or differential force is passing through a point called centroid, and we don't know the location of the centroid. Like what we did, we call it a MRA divided by FRY equals D. but here we call it X bar, okay? And instead of D, we call it X bar on this section. So we're gonna create a differential element, okay, or from calculus, okay? Differential element with a thickness of dx, okay, dx, and the area or differential area, which is equal to the differential force. And also we have the W. W is known as load intensity, okay? W as a function of X. There we go. And then the span of the beam, the length of the beam is L, and the distance from the centroid of this small rectangular area, infinitesimal area, is going to be X, which is equivalent to X bar. X tilde or X bar is equal, okay, in that case. So remember, we went from pressure to load intensity. See that? It changes from P. Remember, the P is what? It's a pressure, which is a Newton per meter squared. If you multiply by the thickness of the beam, you end up with W, correct? Because W is Newton per meter. So if you say a Newton per meter squared times B, which is B is a meter, so you end up with W, which is a Newton per meter. All right, so we go here, in case W is a function of X as the units of force per unit length, and then differential force or differential area is the area of a rectangle is what? Is the width times height, correct? The height is Wx times dx. So that's the differential area or differential force. Consider an element of length dx. The force magnitude df acting on it is given as such. Okay. Then from calculus, we said, okay, and now we wanted to find the resultant force, which is equivalent to total area under this diagram, this loading diagram, which is Fr. Fr means area, okay? Resultant force means area under the loading diagram. Passing through a C, a centroid, C denoted for centroid, okay, of this area, shaded area. And the location of the centroid, or where the resultant force is passing through that centroid and applied on this beam, it's called X bar, the location of it, okay? All right, how do you find the location? All right, this is where we go here, and then we go through a little bit of moment, okay? That's a moment stuff formula. And then we get to this formula right here. Okay, let me go through the derivation, and then we get to this formula here, okay? All right, so this is the formula that is going to help you to find the location of the centroid or the differential force or the force applied to this, what goes through the centroid for the given loading diagrams. This is a loading diagram, incremental load, right? Along the axis of the beam, x-axis. X, W of X, Wx is given to you, is a function like a f of x, like f of x in calculus, okay, function. And then Wx, W as a function of x, dx means differential area, correct? Differential area. Divided by Wx is a function of length, okay, the limit is a length from 0 to some numbers, okay, 0 to some number. That's a 0 to 5 or 0 to 10. There we go. Differential area, if you integrate the differential area, you get the area, correct? Area. All right, so x dA divided by dA, integrals of dA, and this is x W. So this is your fundamental formula when you have been provided with a function. If the geometric shape is not known and you have been given a function, you use this formula to find the location. And then you know that to find the resultant force is equivalent to the area under this curve. So what's the area? You integrate and the differential area, you get the area, which is the FR, okay, which is FR. So you will learn more detail later about the FR acts through the point C, which is called the geometric center or centroid of the area under the loading curve or loading diagram. Okay. All right, so W as a function of X. Example, okay. Please put your seatbelt on for rest of the semester for many years to come. If you are civil engineers, mechanical engineers, structural engineers, You might have a beam or you have a bridge that you pour concrete, and you have a uniform loading on the flat surface of the, of the bridge. So uniform loading. We call this load intensity, which is 400 pounds per feet. For rectangular loading and support, ball support, that's a simply supported beam. So for this loading diagram, a centroid will well defined and shown on the inside back cover of your textbook. If you go to back cover of your textbook, you will find that all this, information or formulas that are well has been established. Okay, established. So what is the FR? The resultant force you take, because this is the load intensity. We said what? It's a pound per unit length or Newton per meters. Pound per feet. So 400 times 10, you get 4,000 pounds. So that's equivalent. Where the location is? 5 feet from the centroid, half of the 10 feet. Okay, exactly in mid span of the beam, length of the beam, 10 feet. Half of it will be 5 feet. If you have a triangular loading, look at this. W is a 100x Newton per meters. X, if it's 0 here, W is 0 at the vertex of the triangle. Okay, this is the wall of the triangle. This is the vertex of a triangle, which is coinciding where the X and W axis start, the origin. Okay, that's the origin. So if I go 100 times 6, I get 600 Newton per meters. So in a triangle, the area of a triangle is a 1/2 the base times height. So 1/2 the base is 3. 3 times 600 is 1,800. So the area of this triangle is equivalent to resultant force that passes through the centroid of this loading curve, or the load under this curve, or the line of this triangle, or I call it loading diagrams. Okay. Now, how do you find the location of the centroid for this type of shape, triangular shape? From the vertex, it's always 2/3 of the base. Okay, the base is 6. 2/3 of the base is 2 times 6 is 12. 12 divided by 3 is 4 meters. Okay, 4 meters. So from the centroid to the vertex, we call it 2/3 of the base. From the wall of this triangle to the centroid is 1/3 of the base. So 1/3 of the 6 meters is 2 meters. So 2 meters is to this side and 4 meters to that side. Okay, there we go. Okay, everybody's clear on that? Clear, all right? So if the function was provided, like a f of x, wx, then you integrate. Do not integrate if the geometric shape is known. Don't need to integrate because you know the area of rectangle, you know area of a triangle, or you know the area of a trapezoid. Okay, all right, so anyway, again, it's a look at the inside cover of your textbook. You should find the rectangle triangle cases. Finding the area of a rectangle is very easy, and a centroid is easy. Note that triangle presents a bit of a challenge. Not really, but they're saying that it would. There is no challenge, okay, but they're saying, but it still is pretty straightforward. All right, so let's go. And I mean, I already explained this. They're trying to explain it like, okay, it says FR is 400 times 10, which we already talked about that, okay, and that's one. Let me just move to the next slide, okay, example. Let me just finish this example, then I'm happy. Make sure that your work is it's as clear, as neat as possible for this kind of loading diagram. Here we have a triangular loading, we have a trapezoid, but this is what we wanted to know. We wanted to apply, we want to find the resultant force for each area. What I will do is I'm gonna come up with area number 1. I'm gonna draw a line in here, and I'm gonna have area number 2, and area number 3 is a rectangle. Area number 2 is a triangle. Area number 1 is a triangle. So I have 3 areas. So I need to have a 3 resultant force and 3 X bar. So X bar 1, X bar 2, X bar 3. FR1, FR2, FR3. You need that to be ready, because when you take the moment about support A, we have FR1 times X bar 1, FR2 times X bar 2, FR3 times X bar 3. So everything is in front of you. Okay? That's called organized work. Find the equivalent force and its location from point A. All right, so we have a distributed loading can be divided into 3 parts, 1 rectangular loading and 2 triangular loading, as I mentioned here. So 1 rectangular and 2 triangular. And determine the overall resultant force of the 3 points loading and its location. Okay, beautiful. Okay, one by one. If this is FR1, we say this is a triangle. It's 1/2 the base times height. The height is 800, the base is 12. So 6 times 8 is 4,800 pounds. Location from the vertex is a 2/3 of the 12, which is 8 feet. So we have FR1, X bar 1. Now we go to FR area number 2. Remember the 800 minus 500, it gives you 300. So this is this part, the wall, this wall of it, this small triangle is a 300. Okay, don't forget. 800 minus 500 gives you 300. Okay, so FR2, this is area number 2 with this color here. Okay, half of the base is 9, and the height is 300, so we got 1,350 pounds. X bar 2 here is a 1/3, because from the wall to the centroid of this triangle is a 1/3 of the base, plus the 12, because we have to go all the way to the A, okay? We have to go from the centroid all the way to the support A, and support A, and make sure you go all the way. So you add 12. So from this point, okay, from the centroid to this wall here, which coincides with point B, is going to be 3 plus 12 is 15 from A. Okay, and then the third area is a rectangular area loading, of height 500. Remember I said this is 500. This is the total for the red is 800. 800 minus 500 is 300. So FR3 is 5 times 9, which is, 500 times 9 is 4,500. X bar 3, which is half for rectangle or square or rectangular shape, half of the base, half of the 9, okay? 9 over 2 plus 12, which is 16.5 feet. So for each resultant force, for each area, we have resultant force, X bar 1, okay? You can just organize it, FR1, X bar 1, FR2, X bar 2, FR3, X bar 3. And we add all the forces, FR1 plus FR2 from FR3, we have the resultant force of all 3 resultant forces. So we have, and this FR1, it was F4,800 times, the X bar was 8 feet. For the smaller triangle, FR2 was 1,350, and this is a 15 feet from that centroid of that triangle. And then for the rectangular loading diagram, it's 4,500 times 16.5. The measurement is 16.5. So the total resultant force for all those forces for each area, you add them up, you get 1,650, or we can say this is 10.65 kip, okay? If you have never heard the unit of kip, means per 1,000 kilo. It's not kilo pound, it's a K pound, because K means 1,000, okay? $1,000, 1K, $1,000, okay? All right, so you got the idea. So if I divide this by 1,000, I get 10.65 kip. And then MRA, resultant moment with respect to support A. See that everything is ready. See that 4,800 times A. Clockwise is positive. See that? Clockwise is positive. 4,800 times A. 1,350 times 50. 4,500 times 16.5. So you get 132,900 pound-feet, or we get 132.9 kip foot or feet, okay? Kip, K-I-P. So this is what the K-I-P is, okay? Kip. So kip is 132.9 kip feet, and then we have 10.65 kip. So in order to find the location, if I create another free body diagram equivalent, So I have one resultant force, the total resultant force, which is a 10.65 kip, and then I take the moment, and I'm going to find out the location of that resultant force with respect to left support, which will be 12.5 feet from me. There we go. Okay, that makes sense? Okay. All right, so that's the end of chapter 4. I'm done, and please practice and all that. Okay, all right, so now, that was too much. Are you ready to go over the exam? Maybe one or two problems, okay? One or two problems. And then I need to, tomorrow is what? Tomorrow is Thursday? Oh my God, this is, we need a Friday also as a part of the lecture. Okay, let me just come up with something here. We're going to have a quiz on Thursday, but also we're going to have a Zoom session, okay? We're going to have a Zoom session. There's two simple problems from chapter 4, okay? Chapter 4, you have from 8 a.m. to 8 p.m. no canvas, only mastering engineering for quiz. Okay, remember some students will just say, oh, why there is no canvas? I said I'm repeating this. Only you do the work for quiz only. Quiz, okay? You just do the work on mastering engineering. It shouldn't take more than 20 minutes, 30 minutes, but you have 60 minutes to do 2 problems, and I'm gonna give you, say, 10 points for each. So that will be total of 20 points for 2 problems, okay? Because we already have 30 points, and this will be 50 points, and then another 50 points will be for the remainder of this summer session, okay? For the quizzes and all that. Okay, is that clear? I'm gonna be posting on Canvas the announcement that there are 2 problems that is going to be open on Thursday, quiz number 2 on chapter 4 only. You just open the mastering engineering for the quiz number 2, and then when you open it, you have 60 minutes to finish it. And please do not just open it at 7, you can open it at 7 p.m., but you might just, I just don't like to go to last. Again, no need to submit your work to Canvas. So you need 60 minutes to take the quiz. If it takes you 10 minutes, all the power to you. If it takes you 60 minutes, that's great. But if you go over more than 60 minutes, it doesn't allow you, okay? It doesn't allow you. That's a limit. Okay, so I'm going to stop the share, and then I'm going to stop the, where am I at here? This here, virtual, choose virtual, no virtual, and then I'm going to go here. Okay. Okay, so I'm going to get rid of that. Okay, item number 1. I call it item number 1 because it might be item number 6 for you, okay? But the picture can tell you everything, okay? All right, so we had a problem with some type of support mounted on this inclined plane, and with 2 forces, F1, F2, with the angles, the angle is what? F1, Phi and theta. The angle makes between F1 and the y-axis. Okay, so maybe the y-axis is more here. So I was doing this, and I just a little bit slanted, but it's going to be perpendicular to this. Okay, y and x are perpendicular to each other. All right. So given phi, which is a 45 degrees, F1 was given, which is 5 kilonewton, and the resultant force 6 kilonewton, which is directed along the y-axis. The objective of this question that I gave you, I wanted you to practice law of sine and law of cosine, okay? I wanted you to practice law of sine and cosine. So the question was to find the force number 2 unknown, and theta was unknown. So we create a parallelogram, okay, parallelogram. This is a F1, F2, this is parallel to this is parallel to that. And now I'm gonna take 1/2 of this parallelogram, and I'm gonna redraw this here. So I have force number 1 and then force number 2, and then this angle is 45 degrees, and I have the resultant force, which is along 6 kilonewton along the y-axis. Assume that this is the y-axis, okay? All right, so, which is that, all right, so. And yes, use law of cosine, okay? You want to find F2, you take the square root, 6 squared plus 5 squared minus 2 times 5 times 6 cosine of the opposite angle, and then you get the F2 of 4.31 kilonewton. Then you're applying the law of sines. You say sine of 45 degree over 4.31, which is sine of 45 divided by 4.31, because now this is 4.31. And then sine of this angle, theta. Theta we wanted to find, divided by this side here, which is a 5 kilonewton. You solve for theta, 55.1. So this was like a gift, okay? Very simple problems, okay? Like maybe 5 minutes from 10 minutes, or less than that. Okay, so this is one item, okay? I call it item number 1 for chapter exam 1, chapter 2, and chapter 3. This was belong to chapter 2. Any questions on here? Is it clear? All right, clear, all right. So we go here. Item number 2, also this is from chapter 2, okay? We have 2 ropes or 2 cable, and it's in tension, okay, with a magnitude of 600 pound and 750 pound from A to C. This is 600 pounds from A to B. And then we have all this specification or the measurement so that you know what the coordinate for C is and the, what would be the coordinate for A, coordinate for B. So I just quickly, I said, okay, coordinate for A is 0, 0, 4. Coordinate for B, point B is going to be 3 minus 3, 2.5. And coordinate for C is going to be 2, 4, and 0. Okay, so that's easy. Then we find the position vector from A to B. So we call it RAB. So it will be AB. So coordinate of the B minus A. B is 3 minus 0, I. Minus 3 minus 0 minus 3J. 2.5 minus 4 is minus 1.5 K. So RAB is known. The magnitude of the RAB is 4.5. Unit vector is position vector over its magnitude. Everything is ready in front of you. You just plug it in. And UAB equals 2/3. Why is that? Because if I multiply this by 2, all the numbers on top by 2, and multiply the denominator by 2, I get 9. So 3 over 9 is the same as 2/3, okay? I, right? You know what I'm doing. I'm just simplifying it. Break it into separate fraction, right? So multiply the entire here inside the parentheses by 2. So 2 times 3 is 6, and this denominator is also multiplied by 2. So if the numerator and denominator multiply by the same number is the 1, right? Is 1. So I didn't want it to deal with decimal, so I have fraction. So I have a proper fraction, proper fraction, proper fraction. So 6 divided by 9 is 2/3, simplify. And the same thing here, negative 2/3, and then 2 times 1.5 is negative 3. Negative 3 over 9 is negative 1/3. Okay, so you know, it's just a simple arithmetic algebra, basic algebra simplification. Okay, you do the same thing, my friend, for unit vector along the force AC. You do the same thing, okay? So you find a UAC. Then you have the magnitude of AC. The magnitude is 750, multiplied by the unit vector you found here. Okay, so here. And then you have the same thing for FAB, so you end up with this here. So you multiply 750 times 1/3 I, 750 plus 2/3 J, you end up with 250 I plus 500 J minus 500 K. Similarly, you do the same thing for force along the, or the tension along the cable AB. So you do the same thing, you end up with this here, okay? Now the magnitude of the resultant, you add the two forces AB and AC, you end up with this. Then the magnitude of the resultant, you square each component, and you take the square root, you get 960. How about the coordinate direction angle? Alpha, inverse cosine of 650, 650 divided by 960, 47.4. Beta, inverse cosine of 100 divided by 960, you get 84. Inverse cosine of minus 700 divided by the magnitude is 960, you get. Okay, I think this is good enough for time being because I got tired of talking, okay? So I will continue on this tomorrow, okay? Tomorrow. So that's it, item number 2. That's good enough. I'm going to, yeah, let me just go back to my, let's see where I'm at. Okay, participants, you share. We don't need to share anything here. And then we go to choose virtual background. We go back to the beach. Okay, all right, so. All right, my friend. I am done with chapter 4, okay? Monday, we're gonna start on chapter 5, and then we go to chapter 6. So exam number 3 will be on chapter 5 and 6, 2 chapters. This chapter 4, everybody should get perfect score, okay? Exam on Monday. Oh, I'm sorry. Oh, this is terrible. Okay. Are we gonna have a Zoom session on Monday that you're taking exam or not? Maybe. What I will do is I will record it for you and I'm gonna post it, okay? I'm gonna record chapter 5 and post it for you so we don't fall behind. Okay, is that cool? So you don't have to come to the Zoom session. My job is to record the lecture and then I will post it for you on Canvas. But tomorrow I'm going to maybe review for the exams, correct? I have a lot of example to go over. If I were you, I will take the quiz in the morning. 9 o'clock, 10 o'clock, 11 o'clock, 1 o'clock, 2 o'clock, okay? And then take the exam. I know some of you might say, I have a job, I have to go to work. All right, I leave it up to you. But if you don't want to come to the Zoom session at 5:30, no problem, okay? But I will have a Zoom session tomorrow because I need to review for the exam. Okay, all right, so Monday exam. Let me see, chat, 2 people on a chat room. Brian, it says yes. Do you want to record this? Did I record? Let me see if I start.